continuing to organize this very nice meeting. So I have changed the title of my talk. I apologize for that, but this I thought would be an interesting thing to talk about. So I'll be talking about some anomalous dynamics during gel coarsening. And basically what I'll try to show is that we have sort of found a understanding of some very curious relaxation process that people had observed in experimental gels. And I'll show, using numerical simulations, how those observations can be rationalized. So this is work done in collaboration with Ludovic Wertke in Montpellier. Okay, so everyone knows about the world of gels, very mundane world of gels, apart from the galactic world. So the thing about gels is that these are low-density soft solids, which are formed by percolating cross-linked networks. So basically, these cross-linkings can be permanent, which is in the case of the chemical gels. So for example, rubber is a chemical gel, or transient or physical gels, so which I'll come to in a minute. And we'll be considering mostly physically cross-linked gels and not talking about chemical gels. But in both these cases, there is this idea of a dynamical arrest, so that these particles are not moving around or the links are not moving around. And so this idea of dynamical arrest is very similar to glasses, what Chandan talked about recently. And so this dynamically arrested state has very nice mechanical properties, which are harnessed in the various applications that you see in real life, including very exotic food. And the objective now is to develop appropriate models which can give us the mechanical properties that one sees in different materials. So, yeah. So then, in the world of physical gels, there are two kinds of gels. One is called the equilibrium gels, and the other is the out of equilibrium gels. So equilibrium gels are like equilibrium liquids, so where there is ergodicity and so on, except that the particles are now connected by linkers and they form a percolating network, and you can have a sol-gel transition where you have disconnected droplets forming percolating networks and therefore an structure. But because these linkers can, due to various reasons, for example, like thermal fluctuations, can come out of one droplet and go to another droplet, there's a continuous relaxation of the network, and therefore you have an equilibrium system. If you have a very dense collection of these droplets and linkers, then you can go over to a glass. And this is a phase diagram that we had derived some time back. So, and the other case, or the more largely explored case, is the case of out of equilibrium gels. So here, what people usually do is you have, let's say, colloidal particles, and you add polymers to it, and the polymer concentration comes as a function of this attraction strength. And so if you're increasing the attraction strength, you go from this, let's say, from the sol phase to the gel phase, which is essentially a phase separation process. Okay, so you have structures which form like this. So this is the gel that they have got in the experiments, and this is the sol phase, which is over here. Now, if you can go to denser in this phase separated region, you can get structures which are very dense, and you really cannot see the voids. And for this system, they also see a glass at very high densities. It's not very clear what happens over here, so we'll also not be exploring this, but these are phase diagrams which are still under study and so on. So the phase boundaries are not very well demarcated, and this is work in progress. So a typical, in a 3D system, you have this kind of a percolating structure that was observed in colloidal gels by this group in Harvard. So and then also there are systems which can go from an equilibrium gel to a phase separated state and so on. So this is the case of laponites and so on. Okay, so what we are interested in is this class of out of equilibrium gels, and there are some very interesting observations that were made by different groups. First work that I know of was reported by Ranjini, who was here yesterday during her postdoc days. So where, if you look at this time correlations of the density fluctuations, which Chandan was talking about, these time correlations could be fitted by this kind of a function, except that this beta was larger than 1. So why is it special? It's special because in typical liquids, you have simple exponential decorrelations, and in glasses, which Chandan talked about, you have stretched exponentials, okay, because of the slowing down. So here you have relaxation processes which are faster than diffusion. so to speak. And so these were also reported in later work in Montpellier, where also they saw similar time correlations and so on. And the other point that this made was that these kind of relaxations happened in large length scales, okay, the small cube limit. So this was the first set of studies. And the problem then was how to understand this. So the people who came up with these experiments, they themselves at some point claimed that these were artifacts. But later on, they did much more analysis, like measuring spatial correlations of the mobilities. And in those spatial correlation measurements, what they claimed is that there are these ultra-long range correlations, okay? So in these kind of colloidal gels, which are aging, so when you have quenched this system into the phase separation region, there is aging that is going on, the structure is changing and so on, you can find these ultra-long correlations in, spatially. And this they contrast with a simple liquid, which is a Brownian liquid, which has very short-range correlations, or even a very jammed structure like a foam, which has correlations which are much shorter than what was observed in this phase-separating gels. So can we understand this? And we think we have an answer. So the system that we're looking at is a glass former. It is a 2D binary mixture. And we have, since we are looking at relaxations which are over large length scales, we look at really large systems. So we go to system sizes of the order of 2 million particles. And so the idea is that we quench from very high temperatures to very low temperatures, so to different temperatures and across a range of densities. So this is the lazy work at mapping out the phase diagram. So if you change your density and temperature, these are the morphologies that you get at very late times. So these are some of the morphologies that you see are very similar to what Subir was talking about yesterday. So you have droplets that are forming or bubbles that are forming and so on. And if you go to, these are at higher temperatures, and if you go to low temperatures and low densities, you can have these fractal structures, percolating networks that are forming, and this is what I identify as a model gel, okay, for my purpose. So, and if you go to even lower temperatures, there are also these kind of structures that are forming, but the temperatures are so low that the dynamics is almost arrested, and this is almost like a fractured state. Okay, so we will be mainly looking at these temperatures and these densities. And the interesting thing also here is that the solid that is forming over here is glass. So this is a gas-glass phase separation, which Shrikant has done some work on or predicted in 2000, and which was later followed up by the group in Montpellier, and we have also contributed recently to this. Which one? Maybe a mistake in my part. I'm sorry. Thanks for. Okay. Sorry. Oops. Okay, so now if you look at the single particle dynamics, the kind of things that Chandan was talking about, so what we look at are the single particle, for example, the mean square displacement, and also the density, this time correlations of the density fluctuations. So what we are looking at is the special point, which I showed you, is this gel, or the model gel that we are looking at. And what we are measuring is this MSD as a function of time, but with respect to the age after quench, okay? So if you are looking at the time after the quench has taken place, then you see an initial ballistic regime, which again, very similar to what Subir talked about yesterday. And so this is this ballistic part. And then at late time, there's a crossover to a slowdown of the dynamics, and because there's a late time arrest of the state. If you go to larger ages, then you have, there is this, again, subdiffusive regime, which again goes over to this slowdown of dynamics at late times. It is in these intermediate ages that you see that there is a regime at which if you look at the exponent of this MST as a function of time, it is larger than 1, it is 1.5, or super diffusive, as we can call, in the transitory regime. Correspondingly, if you look at the time correlations of these density fluctuations, these functions can be fitted with an exponent which are larger than 1, okay? So indeed, as seen in the experiments, we can see compressed exponentials at wave vectors which are small, that is large length scales, and also we have this correspondingly super diffusive regime in the dynamics. So what is happening in the system? In the interest of time, I'll just go ahead. So this is the movie of a 2 million particle system, and what you essentially see as the system is coarsening, and because of the slow dynamics, there is this intermittency effect, so which slows down the dynamics, and therefore you have caging, intermediate caging over here. But eventually, bonds get broken, necking happens, and then again, this kind of structure formation is happening. So when this kind of ruptures are happening, you see this fast relaxations that occur, which lead to this compressed exponentials. Yeah, these are point particles, yes. Okay. So then what we can go on is, so these are the snapshots during the evolution of the system. What you can then do is look at the spatial correlations of the mobilities. So we have one way of looking defining the mobilities, so which I'll not get into, which is very similar to dynamical heterogeneities that Chandan talked about. So what you can see is that as time evolves, these regions of high mobilities emerge, and then these span the system, or large domains are formed, and you can then calculate the spatial correlations of these, and this has length scales. The correlation lengths are very large, almost like the ultra-long scales that the experimentalists talked about. Okay, and if you look at higher temperatures, you see that this kind of mobilities or the emergence of the large mobilities are sort of homogeneous and not heterogeneous, as in the case of the low temperatures. So as a last point, what we also saw is that if you look at the system size dependence of this correlation lengths, what we see is that there is actually this length, the length scales almost scale with the system size, which implies that there is no characteristic length scale for this large these correlations of these large mobilities, which hints at some kind of an elastic origin for this motion that we are seeing, which is essentially a rupture of the elastic network. So with that, I'll stop, and these are the conclusions. Thank you.
Yeah. So, I mean, to what extent in this particular study, this compressed exponential behavior, you're able to identify with aging dynamics as opposed to sort of equilibrium dynamics that may have a ballistic component which is dominant? Because I guess, shall I?
So, no, the point is we are looking at a certain length scale, let's say at a certain Q vector, which is sufficiently large. And if you look at as a function of the age, so this is a dependence on the age, and only in that intermediate age regime, we are seeing this compressed exponential. So which essentially answers it.
Are there other questions? If not, we thank the speaker again.